Welcome everybody. My name is Dominik Hirling and I'm a pre-doctoral researcher in Péter Horváth's group in the Biological Research Center of Szeged. And my main research interest is related to mathematical modeling of cells of various morphologies. But today I brought a topic for you that I think will be instructive or edifying for everyone here, no matter the background. I don't know how many of you have or work with images, probably most of you, so there might be some slides which are very obvious to you, but I think it's an interesting topic anyways. So what I'm going to talk about, first we start with some motivation, why this task is important for us. Then I will overview the most well-known metrics in image segmentation, instance segmentation. Then I will talk about a very interesting phenomenon, how one can really misuse or abuse the metrics that are available in the literature and turn it to your own advantage, let's say. And show how this is a very strange phenomenon that occurred specifically in the field of biological image processing. Then I will show some quantitative evidence how this is very problematic in this field. Then I will also propose some recommendations how this can be overcome, and in the end I will draw the final conclusions of our work. I didn't tell you this before, but we are very proud that this finding of ours got published in Nature Methods, which is one of the most leading journals in computational biology. So bear with me as we dig deep into this rabbit hole. So what's the original motivation? What's the task? We make some images with our microscope, which is annotated by some experts. It is denoted with the green, and we make some prediction, segmentation with our algorithm, which is shown in red, and we want to have some quantitative metric to evaluate how well we performed on this task. Of course, we have various different metrics that we can use. These are not just specific to image processing or segmentation evaluation, precision recall or F1 score, or we also have this kind of modified accuracy, which depending on whether we are talking about pixel level or object level evaluation, it can be called as intersection over union as well. But overall, if we want to evaluate instance segmentation, then these metrics by themselves don't mean anything. First, we have to define the intersection over union, which is determined by the prediction and the ground truth annotation. So the area of the overlap of the two, the prediction and the ground truth, divided by the area of the union, will be the intersection over union. So if they are completely overlapping, then it will be 1.0, and if they are not overlapping at all, then they will be or it will be 0. So let's see what happens if we want to segment these guys on the image. We apply some image processing algorithm and we get our results. So now it's time to evaluate them. We can calculate intersection over union values for the predictions matched to the ground truth, and these are, for example, the intersection over union values you would count for each and every ground truth object. Now the metrics recall, precision, and so on make more sense if you apply it with an intersection over union threshold value. So usually what we do is calculate these metrics like this. So for an intersection over union threshold t, we can calculate the score, and of course depending on how high this threshold is, the recall, precision, F1 scores, and so on will be different. Usually a good balance is to make it 0.5, but there are various techniques to evaluate different detection or segmentation algorithms. Another very important or very well-known metric, not just specific to image processing again, is the average precision and the mean average precision, which is basically the area under the precision recall curve, which are determined by some confidence values of the network or the algorithm that we used. And the mean average precision is related to multi-class classification or segmentation tasks. Okay, now let's get into business. I want to talk about this specific competition, the 2018 Kaggle Data Science Ball Challenge, which is a very prestigious challenge in the biomedical field, and I believe it is organized on a yearly basis, and you can like really publish very good articles if you win these competitions or if you participate. So lots of them were published in Nature Methods, for example. And the task here was to detect and segment nuclei on these images. But why is this competition important? It's because on the web page of the 2018 Kaggle Data Science Ball competition, in the evaluation section, what they said is that the result will be calculated in this way. At each threshold value t, a precision value is calculated based on the number of true positives, false positives, and false negatives. And they show you this formula, which might seem strange because this is not a precision value, because precision wouldn't count the false negatives, right? So it's a bit strange. And then they continue on that they say that the average precision of a single image is then calculated as the mean of the above precision values at each intersection over union threshold value. So this is what you can see down there, but of course this has nothing to do with the original average precision, which is the area under the precision recall curve, right? So and we found that probably this was the main root of the misinterpretations that have been emerging recently. And yeah, they continue that lastly, the competition metric is the mean taken over the individual average precisions of each image. Again, it kind of seems like it would be a mean average precision, but again, this has nothing to do with the original mean average precision. And if this was not enough, you could say that, okay, there was a competition like 6 years ago and someone made a typo, why make such a big deal out of it? But the thing is that this has really caught a lot of attention in a way that very, very influential and highly cited publications are also misusing these metrics. So it's not really an isolated thing. For example, the de facto standard cell segmentation method called CellPose, which was published in Nature Methods, which is, I believe, now around 50 impact factor. They say that, again, for their segmentation algorithm, they evaluated the performance with the average precision metric, which they defined with this, I guess, modified accuracy metric, where the true negatives are not included in the denominator. And also another very state-of-the-art cell segmentation method, Stardist, also claim in their article that they use the average precision with this formula, and they evaluate it across all images as their final score. Another problem can be how you define this, whether you calculate these scores in an aggregated way, so you calculate it across all your images, or evaluate it image by image and then take the average. It's also a source of misinterpretation, as we found. And I didn't even include all the misinterpretations because we found 5 different interpretations of the average precision in the literature and 6 different interpretations of the mean average precision metric. So it's pretty wide, I would say. And also one other interesting observation is that these 3 articles all work on the same 2018 Kaggle Data Science Ball dataset. They all aim to achieve the same thing, segmenting, detecting cells on fluorescent images, and all 3 of them use a different metric. One of them uses the average precision, another one uses the F1 score, and another one uses a classical intersection over union metric, which is, again, pretty problematic. So what are the problems summarized? First, metrics are misinterpreted and multiple definitions coexist with the same name. Even if we somehow fix the metric definition, like, okay, we agree that average precision is this like newly invented something, this modified accuracy, then we can still have some differences between how we evaluate it, like in an aggregated way or in an averaged way. And another problem is that metrics are cherry-picked, and yeah, even if we work with the same data sets, the metrics for evaluation are not the same. So what we did was we contacted the organizers of 3 different like prestigious competitions and asked them to give us their test set annotations, which is most of the time public, and also give us the anonymized submissions of all of the participants, and let us re-evaluate all of the submissions based on various interpretations of average precision and mean average precision, and let's see if they give us any different results. So how do the rankings change if we apply a different but well adapted interpretation of average precision, for example. And what we found is that here you can see the top 10 participants of the Kaggle Data Science Ball with random IDs, and what happens if we change the metric interpretation, this average precision interpretation, to the different one in the literature. So I think it's a pretty shocking thing that sometimes the 5th place can jump back to the 100th place. With other interpretations, it's not so drastic, but it's still a very shocking thing. And here we made some more aggregated results. Basically, one cell is the correlation between two different metric interpretations, let's say. And the more red the cell is, the more correlated the two metrics are. And here down we have more detailed evaluation where every dot is a participant pair, let's say, or where the participant jumps back if we use one metric instead of another. There are very severe metrics which change the leaderboard very drastically, but here, for example, as you can see, the two metrics are quite correlated, but it still doesn't mean that there are no placement switches. So it's still very problematic, even though the correlation is around 99%. So we still have movements between placements. And yeah, we wanted to shed light on this problem with our publication. We also have some recommendations for that. We definitely think that one should omit the use of average precision and mean average precision if they are not using it according to the original meaning, which is the area under the precision recall curve. Instead, I believe that probably a modified accuracy metric would be more convenient for this true positives divided by true positive plus false negatives, because for the accuracy we would need to include the true negatives as well, but in terms of segmentation or object detection it doesn't really make sense. So that's one suggestion. Also, one should very explicitly define the evaluation formula in their results section, and we also gave some guidelines to how one can overcome the ambiguities of this. And of course, when you are working on an already existing benchmark data set, then you should really use the original metric which was intended for evaluation from the beginning, or if not, then you should really reason why you used something different. And then about the final remarks, I introduced some well-known metrics in image processing and image segmentation. We talked about the misinterpretations and how multiple definitions are, or multiple definitions exist for the same term. And there are also many minor alterations, even if the metric is fixed. So if we agree that, okay, this is the average precision, you still have the question of, okay, but what intersection over union threshold you are using? Are you aggregating through the images? Are you averaging through the images? So this leaves a lot of room for ambiguity, and abusing these ambiguities can be severely used for tailoring the results to your own needs, let's say. And yeah, this is all that I wanted to say. This is a collaborative project between many of my colleagues, and thanks for the attention, and if you have any questions, I will be happy to answer them.
Thank you for the excellent timing. That's why if there is one question, then we didn't used to make questions in this section yet.
Okay.
If there is one. Anyway, this is okay. Please.
You show us some examples of the rankings dropping down drastically. Do you also have examples of the rankings jumping up drastically? Because theoretically it's possible that there are a few things dropping down a lot, but everybody else moves up just a little. So I just wonder if you see examples of huge jumps up and down.
Yeah, so I think, for example, here you have one example, metric number 5 and metric number 37. I don't exactly know what these two metrics are, but here you can see that there are some, yeah, they are all over the place, so you can jump up and you can also jump down. Yeah, so there are definitely examples of jumping up as well. I just wanted to highlight some of the like more drastic ones, but I could definitely have picked more of these.
Thank you. So I think it's a very interesting topic, not only in the bioimage analysis, but in many other fields of artificial intelligence. So thank you, Dominik.
Thanks.
And I just